So from the previous video, we have found out the expression for internal energy for a Fermi Dirac gas or Fermi gas. Basically what we did was that we explained the thermodynamic behavior of a Fermi gas, and we defined how does the PV by kT and the N expression, the number of particles for the system, look like, and then we reach the internal energy. Now we are going to find out how does the CV vary with the temperature. So that is what we are going to explore in this video. So CV is equal to dou U by dou T. So we do the differentiation of the equation 9 with respect to the temperature, which will give me, okay, so let me just write it down for your 3 by 2 NKT f of 5 by 2 z divided by f of 3 by 2 z, which on differentiation will give me CV is equal to 15 by 4 f of 5 by 2 z divided by f of 3 by 2 z minus 9 by 4 f of 3 by 2 z divided by f half z. Okay. Now, so this is one expression possible for the CV, for the full range of CV. So now we will look what happens at different temperatures. In dealing with something like that, we already know, based on our discussions from the Bose-Einstein systems, we introduce something called the virial expansions for example, for the PV by NKT, or we used it for N by V also. So here, in this kind of system, if I write down the similar equation, we have already written the expression for the PV by KT, and here if we write it down the expression in terms of the virial expansion, it will be sum over L is equal to 1 to infinity minus 1 raised to L minus 1 AL N lambda cube by G raised to L minus 1. Okay, so this is the expression. Correspondingly, for CV, I can write 3 by 2 Nk in terms of the virial expansion as 3 by 2 Nk, sum over L equal to 1 to infinity minus 1 raised to L minus 1, 5 minus 3L divided by 2 AL N lambda cube by G raised to L minus 1. We have dealt with this kind of expression and its derivation detailed in the Bose-Einstein system. So those who want to remind themselves, they can go back to that section and see and understand by themselves. And now what we can always substitute the values of the virial coefficients, right? That's what. So if we substitute that, we will get the CV is equal to 3 by 2 Nk 1 minus 0.088 lambda cube by GB plus 0.0066 lambda cube by GV minus 0.0004 lambda cube by GV plus etc. So this is the expression valid for CV. What does this expression tell you? This expression tells you that at very high temperature, what will be the value of my CV from this expression? It will be 3 by 2 nk. And not only that, at an intermediately high temperature, not very high temperature, but so-called a decent temperature, so I can write only high temperature, low temperature. Basically, it all depends on your Fermi temperature, which the TF. But based on that TF only, I can tell high temperature, low temperature. But since I had not introduced the TF over here, let me not go into that kind of. So if we confine ourselves to the nomenclatures like very high temperature, at high temperature, what is the value? It's the CV will asymptotically approach 3 by 2 nk. So this is what you will see at high temperature. Okay. Now the question is that what happens at low temperature? Right? For that purpose, we need to consider one of the expressions which we were considering that earlier, which was about the U. See, this is the general expression for U. U is equal to 3 by 2 nkt, f of 5 by 2 z by f of 3 by 2 z. We will use that expression, but before that, you need to be aware of some of the expansions for they call it as the asymptotic expansions. Asymptotic expansions of the Fermi Dirac function, if nu is said, in terms of 1 by ln z. Okay. If you write down those kind of expressions, this you have to by heart. F of 5 by 2 z is equal to 8 by 15 pi raised to half ln z raised to 5 by 2, the 1 plus 5 pi squared by 8 ln z the whole square, the whole raised to minus 2 plus etc. Okay, and correspondingly, similar to that, I can write down the expressions for f3 by 2z is equal to 4 by 3 pi raised to half ln z raised to 3 by 2, 1 plus pi squared by 8 ln z raised to minus 2 plus etc. F of half z is equal to 2 by pi raised to half ln z raised to half 1 minus pi squared by 24 ln z raised to minus 2 plus etc. So these are different expressions. These are the expressions for f nu z expanded in terms of ln z raised to minus 1. Okay. Right. And if we apply this, for example, the equation which we started with was the expression for u, right? And it has got f of 5 by 2 z and f of 3 by 2 z. So if I substitute this equation 14 and 15 into 9, I will get an expression for u. Substitute 14 and 15 into 9. What will I get? I will get u by n is equal to 3 by 5 kt ln z 1 plus pi squared by 2 ln z raised to minus 2 plus etc. U by n is equal to 3 by 5 kt is ln z 1 plus pi squared by 2 into ln z raised to minus 2 plus etc. So you have now you have the expression for u by n, and earlier we have found out an expression for n by v, right? What was that expression? N by v is equal to g by lambda cube f of 3 by 2 z. So if we substitute this new expression for f of 3 by 2 z into that expression, I can write n by v is equal to 3 by 5 kt ln z into 1 plus pi squared by 2 ln z raised to minus 2 plus etc. Okay. Sorry. That's mistake. I wrote down. N by v is equal to 4 pi g divided by 3 into 2m by h squared raised to 3 by 2 the kt ln z raised to 3 by 2 into 1 plus pi squared by 8 ln z raised to minus 2 plus etc. So this is the expression we got by substituting for g of 3 by 2 f of 3 by 2 z into the original expression, which was equation number 5 which we discussed in one of the previous videos. We substitute just that and then we got this expression. Okay. So in this equation 18, if we take the zeroth approximation, which means what? Which means that I am neglecting all the higher order terms, right? Then I will get n by v is equal to 4 pi g by 3 2m by h squared raised to 3 by 2 kt ln z raised to 3 by 2, right? Because I am neglecting all the other terms, right? If I rearrange this equation, equation 19, I can now write kt ln z is equal to, just rearranging, 3n by v 4 pi g raised to 2 by 3 h squared by 2r. Okay, so this will be the expression I will be getting for kt ln z. Some of you might be knowing this, or maybe I will have to tell you, this is actually expression for your Fermi energy. I have not introduced that Fermi energy expression till now, which I will be doing in one of the videos to come. But this term is actually equal to Fermi energy. This right hand side is the expression for Fermi energy. So therefore, I am talking to you about some kind of a chemical potential where this say, what is kt ln z? That's the question, right? Kt ln z. Kt ln z is what? Kt into z is equal to e raised to minus mu by kt. So if I found out the ln, kt into mu by kt, cancel, which will give me a chemical potential value, mu. Since this came out through the zeroth approximation, I can define it by mu 0 is equal to some energy called the Fermi energy. So this right hand side is actually the expression for Fermi energy, which I will be introducing that later, then you will understand it better. So whatever the case, this is the takeaway. Kt ln z is equal to Ef. Now if I take the first approximation, or the next approximation, I will take one more term in equation 18, right? In that case, if I rearrange and then if I write it down for the expression for kt ln z, which is again a mu, of course that was mu 0, this is mu now. This I can write in terms of the Fermi energy, Ef into 1 minus pi squared by 12 kt by Ef the whole square. So note that this expression is, you have to take this part also, and then we are writing it in terms of the Fermi energy, and this defines the Fermi energy. Okay, so if we substitute equation 21 into this expression for u by n, because instead of this kt ln z, we will now substitute this equation 21. If I into 17, into 17, we obtain u by n is equal to 3 by 5 Ef into 1 plus 5 pi squared by 12 kt by Ef whole squared plus etc. Okay, and if I find out the expression for Cv based on this above expression, in equation number 22, I will get Cv by Nk is equal to pi squared by 2 into kt by EF plus etc. Okay. Now equation. So now we have an expression. So what was the assumption in all these cases? We started with this assumption that what happens at low temperature. Okay. And we expanded made the asymptotic expansion of F nu Z. And of course we know that what happens at high temperature. And at low temperatures, now this expression is telling me that CV is directly proportional to T. CV is directly proportional to T almost. CV is proportional to T. Now, and we we know that CV will be 0 at as T tends to 0. So now we know 4 kinds of informations. One is that CV tends to 0 at T tends to 0. CV is directly proportional to T at lower temperatures. CV will be 3 by 2 NKT at very high temperatures. That is a classical regime. And at the so-called high temperatures, that will be an asymptotic approach to that value. So if we combine all these ideas and we make a plot, the y-axis we have CV by Nk, and in the x-axis we have T by Tf. I have not introduced the Fermi temperature. The Fermi temperature is the temperature corresponding to the Fermi energy. So if I put this value as equal to 1.5 y, this is 3 by 2, right? CV by Nk. So 1.5. That means at high temperature it has to be like this. And for over here, it has to behave like, at very low temperatures, it has to behave like CV directly proportional to T. So if this is the graph corresponding to the linear progression of CV with respect to temperature, combining all these things, I can draw like this, showing the connection between the temperatures, connection between the CV and the, this is 1, 2, 3. It's T by Tf. Huh? So that is it. So this represents, so these red lines actually represent the CV directly proportional to T. And this is almost the graph of CV by Nk for a Fermi Dirac system. Okay. Rest in the next video.